Hello, everyone. I'm Stéphane Thiell. Apologies for my voice. I'm not used to the rainy weather anymore. So I work at Stanford Research Computing, and I'm research storage lead there. And I'm going to talk today about a topic I believe will be of interest of many of you. It's hardware upgrade practices with Lustre. First, I'm going to start with the Lustre updates at Stanford. I haven't done that for a few years now. So we have multiple compute cluster and storage system based on Lustre. We have two main Lustre-based computer cluster. The first one is Sherlock. It's our shared computer cluster for sponsor research. It's a condominium model. It's very common in US universities when the university provide a core, a pool of node. It's like the free tier, and then you can, researcher or principal investigator can purchase their own node and contribute to the cluster. So we provide a catalog of nodes, of GPU nodes, and the cluster is about 1,500 compute nodes across two fabrics. So the way we could do a whole presentation about how we lifecycle Sherlock compute nodes, because we add new IB fabrics and we remove old ones, but we keep adding nodes. It's like a ever evolving cluster. So Sherlock also has more than 100 nodes, GPU nodes, with some with LNet multi-rail. So the slides should be available. You can click and go check more info about Sherlock. And the second Lustre-based cluster we have is SCG. It's a set of resources for a service center, the Genetics Bioinformatics Service Center. It's more modest, but it's very interesting on the Lustre side because it's all Ethernet. So mainly 25 gig Ethernet nodes, but it's connected to Oak that I will present at 200 gigs. We also have a SGI UV300 on that cluster. So that's the Lustre clients, the two clusters. And then we have two major Lustre storage systems. FUR, which is Sherlock's Scratch file system. So it's home built. We design it. It's a high-performance storage system for temporary data. So you all know what Scratch is. We purge after 90 days based on the data version. So if the file is not modified, if the content of the file is not modified after 90 days, it's removed automatically. So FUR is about 6 petabyte usable, and we have been using Project Kota for many months now. We're very happy with that. But it was deployed in 2018, so all OSs are currently HDD based. The second Lustre storage system we have at Stanford is Oak Storage. It's a global capacity-oriented Lustre file system. So we build it with large I/O cells. So the largest are currently 11 petabytes each. It's a rack. We maximize the number of disks versus the CPU. It's about 40 petabytes usable, but before the end of the year, it's going to be 51 petabytes usable at least. We have a lot of demand. And at this scale, it's very large for a university to have that much data on one namespace. We have a very strict inodes per volume ratio, so 150,000 inodes per TB. And that's allows us to maintain control on the file system. And even though we have 2.1 billion inodes used right now, we still we avoid like crazy amount of inodes generated by user by mistake often. So that's a fact I wanted to mention. The other interesting fact is we are using QoS, so NRS TBF per GID on the OST and OST-IO services. And we spend a lot of time finding the right settings for NRS, and we are quite happy with this setting now. We are setting rates limit per group, so basically per org space that we allocate, but the rates is in function of the space they purchased. So if a group have 1 petabyte, it will have more. It will be allowed to do more RPCs. And Oak is offered to our researchers as a service. And so it's not free, it's for a fee since 2017. And all this space, I mean, it has been very, very successful. They are very happy. So I made this diagram to summarize. At the top, you have the Lustre clients. At the bottom, the Lustre servers. So we have Sherlock on multiple IB fabric. We have the SCG cluster. We have also Oak gateways, because Oak, this big system I just mentioned, some groups want to access it directly via specific protocols, not from the cluster. And for example, SMB access is very popular. So we have those VMs that run on a KVM hypervisor farm, and we use a virtual function, so SRIOV, for that. So Oak gateways are also Lustre clients. And we also have a backup swarm. So we have like a pool of nodes managed by Docker Swarm to back up Oak to the cloud. It's not the default. You have to have a cloud account. And so some researchers have cloud credits, or sometimes they are scientifically obligated to back up their data to a remote area. In that case, we help them and we orchestrate like the REST backup to the cloud. So clients at the top and server at the bottom, Fur and Oak. And the next slide, we reveal the Lustre version we are using on those systems. So we are still mostly using 2.12.9, but on Sherlock, we have completed the full upgrade of all Sherlock clients, so the 1500 Sherlock client to 2.15.0. And we have been happy with that. It has been quite smooth. So very happy about 2.15 clients so far. Next step will be to upgrade the servers. So that's it for the update. The next part of my presentation, there will be 2 parts. The first one will be, I will discuss how we manage the life cycle of hardware on Oak storage. And the second part will be how we plan to upgrade Fur or Scratch file system. So Oak, Oak, it's like funded through a university service center. We don't have big central funding for that. So it's like constantly evolving storage system. And we have to answer the demand, right, and manage the systems. So basically what we do, the hardware lifecycle on Oak, it's basically 2 things. It's we add storage when we need to accommodate more demand or replace old storage, and we remove storage when the storage, the hardware is too old, or we reach the end of warranty, or we are not able to source any spare parts anymore. So it looks simple, right? We add and remove storage. Now the method we use for adding new storage, so we prepare new OSS, new OSTs, adding is easy. In Lustre, you mount new OSTs. We always use, in our case, we don't reuse OSTs, so it's important to mention that we are using always higher OST indexes. So when we add new storage to Oak, we use increasingly in OST indexes. The harder part is to remove the old storage. That's because Oak now is more than 5 years old, so we have started to remove, and we removed already old equipments. And so this problem came up. So we remove old storage basically in the recommended way by the Lustre manual. We set the OST in no create mode well in advance for the storage we want to remove, so that there won't be any recent files stored that. So when you set that on the MDT, the MDT doesn't allocate new object on those OSTs. And then after sometimes we need to empty the OSTs we want to decommission. So we migrate data, and we do that with LFS find and LFS migrate. So recently I've been using LFS underscore migrate more because we also restripe files. We have some very large files and on Oak, so it's a good opportunity to use LFS underscore migrate. We have some nice options to set the striping in function of the size. This is because we didn't have PFL at the beginning. So most objects on most files that are located on the first OSTs are still using the legacy, plain layout. So it's important. I mean, it's a good opportunity to restripe them. And then we deactivate, when the OST are confirmed to be empty, we do a last check with LFS find. We deactivate the empty OSTs with LFS conf param. And the next step is to permanently remove the OST from the file system. And for that, we use a new command that is lctl del OST, so for delete OST. And I will talk about it in just a moment. It's worth noting we are removing OST indexes from the lower indexes, and we are not reusing them. So basically, we have a sliding window of indexes over time. So I made this diagram to understand a little bit better. You can see at the left, we started with IOCL 1. We added 48 OST. Then, because we had I put the need of new IOCLs is driven by demand. So yeah, we have more researcher interested in storage. So we had a second IOCL, a third, a fourth, and five. So over time, at the beginning, we only add OSTs. But after some point, the warranty, you can see, after the first IOCL, the warranty was 4 years because of Quanta JBods. We need to get rid of it. So we started to remove OST now while still adding more OSTs. So we have this game of removing, adding. Of course, the OST we add now are much more larger in capacity. In IOCL 8, it's like the equivalent of 3 or 4 times IOCL 1 in volume. But that's the big picture of the life cycle of Oak over time for the OSTs part. The warranty time may vary a little bit. You can see that lately we have been using Western Digital JBods, which it's nice because they came with 5-year warranty, so it's slightly longer. That's it for the life cycle overview. So to come back on LCTL Del OST, it's actually a development we made in collaboration with WarmCloud, and Andreas, who is here, actually wrote a long time ago some specification in a Jira ticket, the LU7668, but nobody was developing it. So we said, oh, we need that, because Del OST, what it's doing is like you can remove OST permanently without doing a write conf. So if you don't know what a write conf is, the normal way, until now, the way to remove OST was to shut down everything, clients, servers, and you do a write conf by forgetting, the OST you want to remove. So you basically register all your targets again to the MGS, and that it's forgotten. But that's imagine we have to do that at each time we have to remove OST, that would not have worked. So Del OST is a great alternative to that. We can do everything live. So thanks to Andreas for the help reviewing the patch, and it's landed on 2.16. And a backport is possible, but I wanted to mention that while using Del OST in production, we hit a bug, because basically Del OST will cancel record, in the config log of the MGS, and propagate this change to MDTs and clients. And we discovered there was a bug when those cancel records were propagated. And so Etienne Ojam, who is in this room, thank you, Etienne, helped for fixing that problem and fix this bug. But If you backward it, you need the patch for LU 15,000. And finally, a side note, Stanford Research Computing is going to has submitted a paper to the HPC CISPROS 2022 as supercomputing, and Dell OST is actually part, and it described it in this paper. So that I encourage you to check it out when it's out in November. That's the part. So now the last part is different than Oak. It's we need to upgrade for our Scratch file system. It's old. It has served its purpose, but we see. I mean, you have probably all seen like new kind of jobs, deep learning jobs, or we see also we have a lot of cryo-EM, the cryo-electron microscopy, which work on very large data sets in a random I/O fashion. So it's time to have some flash on the OST side. And so we advocate for a flash upgrade on offer. So it's different than Oak, because this is more like we get a bucket of money to upgrade for. So the goal in this upgrade is first to increase IOPS, because all our OSTs are based on HDD today, and if the data set doesn't fit in the OSS cache, we are limited by the IOPS from the drive. The second goal is to increase the bandwidth, because we have seen a plateau of bandwidth because just HG100, we have server with HG100, we need more. And the volume also, we have more, the user base, our user base is growing, and researchers really don't want a retention period less than 90 days. And some have been very vocal about that. So even though, 90 days can seem long to some of us, they really are not ready to have less than that on Scratch. So we would like to keep 90 days as the retention period for the data on Scratch. But currently our Scratch is almost full. We are at OSTs are 95% on LDiskFS, it works well. So 3 goals, it's a lot to ask, but we are going to do that in an easy way. I think it's like to replace our current JBODs and server with SSDs. So nothing as fancy as the previous presentation about NVMe over Fabric for now. So let me present what we are going to do. We also limited in footprint, so we are going to do a live in-place upgrade. So FUR has 8 I/O cells. We are going to upgrade each I/O cells live without downtime. That's our goal. So we figured out a way to reuse the same footprints, and we are going to remove the old HDD and put a new I/O cell. So this is an example. So our project will use the Seagate Exos E platform. So basically it's a JBOD, a JBOF, and with SAS drive that are SSDs. And the goal is to use, like today, MD-RAID on top of that. So we'll see the challenges with that in terms of performance. But we also are going to upgrade the server, so we'll have HDR200, PCI Gen 4, and multiple SAS cards to have the back-end bandwidth. So the way, so we have the principle of minimal disruption, as I said. Users already have data on Scratch, and they don't have time to copy data to another file system or something like that. So our goal is to bring new performance by upgrading those I/O cells step by step. The goal is to just, over time, end up with at least twice the performance, but without downtime, without disruption. So this has started actually because we just received the hardware for the first I/O cell. So we have set the first I/O cell in no create, and because this file system is purge, we just use the purge and we wait 90 days. And this is a graph, a usage graph of OST 0. You can see we just wait and those objects are deleted by the purge. over 3 months. So when I'm back in office, I have to see, because it's not fully at 0, so there must be some files remaining. Could be files that, the user keep writing to it. In that case, the data version change and the file modified, and it's legit, it stays on the OST. It's not purged. So once we have emptied those IO cells, we will retire those IO cells, those OSTs, with Dell OSTs, of course, and replace so the hardware, the server and JBOD with the new hardware. And then we add the new IO cell to the file system, and we put the new OST in production. After some testing, there will be full flash, and we rinse and repeat for each IO cell. Ultimately, we'll have we expect a performance boost of course, bandwidth. IOPS will be hopefully magnitude higher than today, and also usable volume, because SSDs we are going to use like 15.36 TB SSDs, which is much larger than the drive we had, the hard drive we had from 2018. So it looks like this, the first IO cell. So this is a view of the 2 racks of fur, and when we replace the first IO cell, it will look like this. And then we replace the second, replace the third, fourth. So, and we'll continue like that until the 8th, okay? And then in the end, we will end up with FUR 2.0 with full flash OSTs, and a total of 768 15 TB SSDs, and almost 10 PB of usable space. Now, we only have the budget for half for the next year, so we'll see if we can do that fully. But so we might have some period we will have a period with mixed SSDs and HDD. That's why the presentation yesterday about hot pools was very interesting to me. What are we going to do during that time? The best use of the storage during that time. But ultimately, we really want to have to not have to worry about tiering and migration, and have a full flash scratch file system, which will accelerate all jobs basically on the cluster. So it's a win-win for everybody. And that's it for my presentation. Thank you. Any questions?
Any questions from Stéphane?
How do you manage the fact that when you add new OST, they are empty, and then Lustre allocate everything on those few new OST compared to the file system, so you have maybe less bandwidth at this time?
You mean for FUR when I remove the ISL, or
whatever? When you add new OST to one file system, then most of the objects are going to be allocated on this new OST. So you have only few OST working, and then you have a problem about the
That's a very good point, and that might be an issue on FUR. On Oak, we have NRS. It's not for high performance. It's like longer term storage, and we see definitely when we add new OST, and we try to add enough OSTs. Usually we try to add a full rack to add enough OSTs so that they can handle the load. But definitely Lustre will use them first,
Yeah, and then you don't try to force a bit the rebalance of the file system?
So on FUR, on Oak, we know it works because it's not like a heavy-duty file system. But on FUR, when we are going to put this new IO cell in production that has empty OSTs, of course, all the workload will go there. So it will be full flash versus hard versus HDD, so might be able to, maybe it's a good stress test for it, but it will fill up very, very quickly. So
because the risk is that the user will have not the same experience every time they use it, depending on the OST.
Yeah. So they are tunable for, we could...
Yeah, but it's pain for the admin.
yeah. But we might have to look at this and see if we can disable, the space, smart space allocation for Lustre for a while, or to force a round robin allocation instead. Yeah. Very good point.
Good luck.
Any other question? What about the MDTs?
Yeah, it's a good point. This presentation, have you noticed, only cover the OSTs. The MDTs, I'm waiting for OneCloud to land to land the FLR for MDT, like in 2018. Because that would be great for upgrading MDT, you know? You copy your MDT and then you get rid of your old hardware. But today, it's difficult. We don't have a magic solution to do that without a downtime.
You can do it if you have LVM, you can press. Sorry. Yeah, if you have LVM, you can use that to migrate the storage underneath the MDT essentially, and then, you know, I've done that at home. Granted, not very high load, but you know, use PV move, and then you can replace the storage without taking the downtime. You'd still have to have the you know, the node is not going to be replaced, right?
And all MDTs are quite large. On Fur, they were designed for DOM, so they are like 10 TB MDTs. So it's a challenge. Yep.
You have quite dissimilarly sized OSTs.
On Oak, yes.
Yeah. Do you experience any performance degradation as a result of that
No.
quite notably dissimilar size?
No. Again, Oak is not like or Scratch. It's like it's not the high performance file system. We found out that Lustre is making very good use or unbalanced OST size. The first OST are 64 TB. You know, our latest is like 192, I think, TB. And even though the OST size is different, Lustre does a good job at managing that in a good way.
You don't suffer bottlenecks on the node network side because you've got vastly
haven't
different
noticed that.
allocations.
Yeah.
No, okay.
But it's something that could happen with Fur because the OSTs, OST flash will be bigger. But there will be flash, so flash-based. So
yeah, your bottleneck's in a different place.
yeah.
Last question? Nobody? Okay. Thank you, Stéphane.
Thank you.